Thank you for the introduction. It's my honor to talk over here. I hope that in the near future I'll be able to visit you physically. So the topic I would like to share with you today is some of our recent work on ACS. So in this talk, I'm going to briefly review the ACS problem and show some of our recent works in the past 2 years, mostly CCS papers. And then I would like to share some of our recent works on proof of stake, which I thought some of the people in the audience might be very interested because I see a lot of overlapped interest. So I will begin with the definition of ACS. Many of you are probably very familiar with it. Asynchronous common subset was originally known as the agreement on a core set problem for multiple computation. It was proposed by Ben Orr, Canetti, and Goldrich. But later on in 1994, Ben Orr, Kamler, and Revin formally proposed the notion of asynchronous common subset. And after many years, it's a problem that it's often named differently. So for example, in Kashin's paper, it was called core set problem. And in the paper by Correa et al., it was also called vector consensus. But they are all ACS. Problem definitions are almost the same. And in many years was studied theoretically and started from 2016. A lot of practical works are developed in recent years. And based on the assumption, we can in general divide it into unconditional setting and computational setting. For the unconditional setting, the nice thing about that is information theoretically secure by design, meaning that if we assume a revenue dealer that shares a common coin for us, we don't need any cryptographic functions to build the protocol. But we do sometimes need to assume authenticated channel, and that's kind of the assumption on the network side. So many of my works focus on the unconditional setting, while there is also a series of papers that study computational setting. So the definition for ACS is that every replica in the system proposes one value, and all replicas are correct replicas. They agree on a set of values. Usually the set of values is n minus f, but sometimes in different primitives, we can change it to other threshold as well, for example, f plus 1. So that's kind of the definition for ACS. And other than the validity definition, agreement and termination are pretty standard for consensus, which pretty much means that every correct replica decides the same value and they eventually decide. There are different paradigms for ACS. In general, they can be divided into 3 types. The first one is the BKR one, the most classic one. It's followed up by many works. It's unconditional setting, and the other one is DKPS. It's in the computational setting. There's also a third track, which is MBA, multi-value Byzantine agreement based. But this paradigm is not well developed. So most of the recent works follow the BKR paradigm and CKPS paradigm. In terms of the building blocks, they are built from different underlying primitives. Mostly BKR paradigms protocols are developed based on reliable broadcast and binary agreement. I see there's typo over there. But for CKPS, it's usually developed from a consistent broadcast, multi-value validated Byzantine broadcasts, and those type of primitives. In terms of the underlying primitives for BKR, I would like to briefly review what they are. The first one is Byzantine reliable broadcast, RBC. So RBC pretty much means that a sender sends a message to a group of replicas, and we want to ensure that all correct replicas in the system deliver the same message. Like if the sender is correct, everything's very natural. Like all correct replicas will deliver the same message. But the issue is that the sender might be incorrect. So the sender may send different messages to different replicas. It may not send message to some replicas. In the end, we want all correct replicas to make the same decision. They either deliver one of the M message that is also sent by the sender, or they deliver nothing. like in the asynchronous setting, it means that if the sender is incorrect, the protocol may never terminate. And we can simply say that the replica delivered a bot message. Another primitive that's also very useful is Byzantine consensus. So it can be in general divided into two settings. One is a binary setting, one is a multi-value setting. So in the binary setting, ABA, every replica provides 1 bit as input, and eventually they decide on 1 bit. This bit must be proposed by one of the correct replicas. And in multi-value setting, it can also be classified into several different types. So the most well-known ones are multi-value Byzantine agreement, which is only a multi-valued version of ABA. And another one is multi-value validated Byzantine agreement, which the validated here means that the input is validated by something. It can be a signature, or it can be validated by an internal state of the replica. And a brief review about BKR paradigm, and a lot of you are probably very familiar with it already. So the idea is that we want to decide on a set of values, right? So every single replica can use RBC to first disseminate its proposed value. And it's possible that every replica delivers value or like they do not deliver the value, right? So it's a binary decision, right? So after an RBC instance, every replica uses an ABA to decide whether all correct replicas, or at least a large fraction of correct replicas, have delivered some value in the RBC instance. So in the end, we use RBC and ABA to transform an agreement problem to a binary decision. And in the end, if some replica outputs 1, it means that we can safely deliver the message proposed by the corresponding sender in the RBC instance. So BKR actually employs n-parallel instances like this. So in the end, for every ABA instance that outputs 1, we use the corresponding value in the RBC instance as one of the output for the agreement core set. Right, so that's kind of the general idea behind this. A naive solution over here, which is also the challenge BKR addresses, is that it's kind of very natural to think that if one RBC instance ends, every replica can start to vote 1 if it has already delivered some message, or vote for 0 otherwise. So if we can employ n-parallel instances like this, we can naturally deliver all those corresponding values to form a core set. But the issue is that if we, in the asynchronous network, there is a malicious network scheduler that can schedule the messages received by the replicas. So it's possible that the scheduler can manipulate the messages such that all ABA instances will output 0. So in the end, the system has 0 throughput and ACS outputs nothing, right? So the way how BKR addresses this problem is that it actually employs two subphases of the ABA. So in the first subphase, every single replica waits until at least n-f ABA instances output 1. And after that, every replica starts to vote for 0 for the rest of the ABA instances. So in the end, all ABA instances are guaranteed to output, and there is guaranteed n-f ABA instance that will output 1. So we naturally achieve the validity probability of the ACS, right? But unfortunately, for this paradigm, ABA phase becomes a bottleneck. So actually, this is a study in Dumbo, CCS 2020. It was found that the ABA phase may occupy like over 90% of the running time. And it was actually also our observation as well. So it's quite often that when we check the log, we tested the BKR paradigm, and that some of the ABA instances get really unlucky. So it terminates in like over 20 rounds. So in the end, the latency becomes extremely large, only because of the ABA. So actually, like in next, I will show some of our recent works in ACS. So in the past, we have done several works on ACS problem. So here I only show the works that strictly follow the BKR paradigm. So in different works, we try different things. Like for example, in BIT, we try to use different building blocks for RBC and ABA and even erasure coding part to see whether we can build some system metric for the ACS problem. For example, we provided one version that is read optimal and one version that is storage optimal. But still, again, ABA is likely the bottleneck of the progress at scale. So after that, we started to think about the problem on how we can use the design of the protocol to naturally avoid these high ABA overhead. And recently, like CCS 2020, 2023, and Usenix Security 2023, we try different kind of things along this line of work. So in this talk, I'm going to focus mostly on pace and spin, and briefly mention what we did in Waterbear. So for pace, when we started the problem, so one thing we quickly noticed is that as the ABA gets really unlucky, this phase is very large, right? So one natural motivation is that can we make the naive but incorrect paradigm correct, right? So if we can naturally make the ABA phase fully parallelizable, then we can probably already reduce the overhead of the ABA phase a lot, right? So in this work, what we did is that we proposed a new primitive called RABA, reproposable ABA. So using RABA, we were able to really make the naive but incorrect paradigm correct, and we were able to reduce the overhead caused by the ABA phase by a lot. Like recall that in the BKR phase, the overhead for ABA phase might be up to 95% to 97% of the running time. In pace, we were able to reduce it to like 20% to 80%. Right. So what we did is that we proposed the RABA primitive, and we were able to almost transform every single ABA protocol into a RABA protocol. So it's kind of quite flexible framework that we can almost adapt every single BKR protocol into one that is in the pace framework. So a brief review about the primitives, right? So for those of you who are not that familiar with ABA, might be very difficult to understand, but I kind of would like to share some of the intuition here. So the idea is that we allow every single correct replica to change its vote once, and we call that event repropose event. So this RABA primitive is biased. We can either make it be biased towards 1 or be biased towards 0. Like in this framework, we want to make it biased towards 1. So in the for it to happen, the repropose event is designed in the sense that every replica that proposed 0 is allowed to repropose 1, but not vice versa. So according to this kind of new definition, we are able to have 3 new properties that are different from the conventional ABA properties. So the one unique feature we need is a bias validity property, and that's a crucial fact that makes the pace paradigm work. So the idea is that if f plus 1 correct replicas propose 1, any correct replica will decide 1. Right, so this is quite different from the conventional ABA, because usually we require all correct replicas to propose 1 for them to decide 1. Right, so according to this change, we are able to make a lot of difference for the framework. And to make it work, we also need to design 2 additional liveness properties. One is unanimous termination, the other one is bias termination. The bias termination is a very unique property for RABA, so it essentially needs every single correct replica to either propose 1 or repropose 1. So in the end, terminate. So I will explain why that's the case later. So the way how we build RABA is that we want to make it biased to achieve the nice property, and we also want to make it fast. Right? So the idea is that if all correct replicas, or at least f plus 1 correct replicas, propose 1, the protocol might be able to terminate in only 1 step, and it's even coin-free. There's no need to flip a coin in the first round. So on the left-hand side, it's a typical protocol, the MMR workflow and the Cobalt ABA. A lot of the practical ABA protocols are built using these two protocols. So it roughly works like this, where replicas exchange their votes several times, and in the end they decide. And in Rava, what we did is that we have several generic strategies to transform an ABA into Rava. So the first strategy is that if some replica proposes 1, it can directly broadcast all the votes for 1 in this protocol. So it immediately sends all the messages over here. The next thing is that if one replica reproposes, it pretty much does the same thing, right? If it has not sent the vote before, it will send the vote out immediately as well. And that's kind of the second strategy. And third strategy is that the coin value for round 0 is set as 1. So we only need to make like 3 changes like this for the first round of the protocol to make it a Rava other than ABA. To see why we can achieve the nice properties that we need. So to achieve bias validity property, it essentially means that, say, every single correct replica that proposes 1 directly broadcasts the b-val 1 vote, aux 1 vote, and conf 1 vote, right? So in the end, no one will be able to receive a minus f conf 0 votes, right? So in the end, it's not possible that any correct replica will enter the next round with 0 as a vote. So in the end, it's very natural to see that the protocol will directly decide 1 in the end. And that's kind of pretty natural. But another unnatural thing is the termination issue, right? So here is only an abnormal thing, where if fewer than f+1 correct replicas propose 1, it's possible that the protocol may halt forever like this, right? So we have more explanation in the paper. So if you're interested, you can look at those examples in the paper. But the brief idea here is that to make the protocol live, we essentially need every correct replica to that are previously proposed 0 to repropose 1 to make the protocol live, right? So the idea is if correct replicas will change their votes to 1, then we will be able to proceed to the next phase. So this is kind of the generic idea behind this transformation. Putting the PACE framework, what does it mean, right? So the first thing is that termination, right? So the idea is that if one correct replica proposed 1, it means that it already previously delivered some messages in the corresponding RBC instance, right? So think about this example as Rava 0. It means that replica 1 already delivered some message in RBC 0. So if this is the case, according to the agreement property of RBC, we know that every correct replica, although even if they have not delivered any value yet, it will eventually deliver some value in the RBC instance, right? So putting this framework, it means that if some replica previously proposed 0, after it already delivered some value in the future for the RBC 0, it will repropose 1 for Rava 0 as well. So using this nice property, it makes Rava a perfect fit to be used together with RBC. So in the end, we are able to guarantee that every single RBC instance and every single Rava instance will terminate in the end. So that's kind of a nice property about liveness. In terms of safety, right? So the validity property, we need some Rava instances to output 1 to guarantee throughput and to guarantee the validity property of ACS. Right. So one thing we noticed is that for this PACE paradigm, if we count the number of instances where at least f+1 correct replicas have completed some RBC instances, after each of them completed at least n-f RBC instances, we come up with a solution that for at least f+1 RBC instances, and for each instance like this, at least f+1 correct replicas have already delivered some messages in each of the RBC instances. So in the end, we can guarantee that at least f+1 RABA instances will output 1. So in the end, so the validity property here in PACE we achieve is slightly weaker than the standard notion of ACS, where we only guarantee f+1 output instead of n-f output. So that's kind of what PACE can achieve as an ACS primitive. In terms of evaluation, we evaluated many protocols, right? So we transformed several ABA protocols into RABA, and we evaluated and compared it with BIT, Dumbo protocols, well, state of the art at the time. So what we found is that PACE actually can achieve a pretty nice result, especially when n is small, right? So when n is like 1, n is 4, like with one faulty replica, the performance of PACE is already 5 times that for Dumbo and 1.7 times that of BIT. When n is large, the protocol still outperforms all the previous protocols in the BKR paradigm, almost twice of the throughput, but almost 4 times of the throughput. But if we compare it with protocols like Dumbo, it only achieves almost 2 times of the throughput. So that's kind of PACE. So
well,
after
quick question.
Oh, yeah.
So the speed up, is it coming from the fact that you don't have this kind of extra weight before you can input stuff into the Byzantine agreement, or does it come from the fact that the RABA runs faster than the ABA?
Well, I think both, right? So so in the failure-free case, I think the speed up mostly comes from the fact that RABA is much faster than ABA, right? Because there's no failure, it's almost guaranteed that all RBC instances can terminate like in a very close short time window. But in the failure case, which we also evaluated in the paper, I think partly comes from the fact that like there's only one ABA phase, if that makes sense.
Okay, thanks.
Mm-hmm. Yeah. Yeah, so after we finished PACE, we also tried another interesting thing, because like the protocols in BKR paradigm comes information theoretically secure by design, right? So there's no need for any cryptographic functions. But in practice, for most of the practical ACS protocols ever implemented today, people use threshold signatures or threshold PRF for common coins, right? So that's still cryptographic functions. And when we actually evaluated the protocols, what we found is that when n is large, like probably larger than 100, the overhead caused by threshold signatures and threshold PRF cannot be ignored anymore. So one thing we tried is that can we really build an at least quantum secure or information theoretically secure protocols, like ACS protocol. So we what we tried over here is we actually want to really avoid the use of common coins at all. So like for if we have a closer look at the paradigm, RBC can be made information theoretic or at least quantum secure, right? So the minimum thing we need is to use hash function. And we can even remove the need for using hash function at all by using the Brashov's broadcast. That's the most classic one. Although it has a very high communication complexity, it's information theoretic. So we always wonder how it performs, right? So we actually implemented it and tested that. So that's kind of easy for RBC. But for RABA, it's a little bit challenging, right? So for ABA, we have to avoid the use of threshold signatures and threshold PRF. So in the end, we thought we came up with one very interesting idea is there is a very classic way of building ABA, which comes from local coins. Like in this problem, every single replica flips a coin locally if needed. And if it happens that all correct replicas flip the same coin, they can decide. I mean, the challenge over here is that it has exponential complexity, right? So in many years, people have been thought that is very impractical. You will never be made practical at all. So one thing we tried over here is that can we make it practical? So what we did is we actually built a more efficient ABA protocols from local coins. So briefly speaking, we built 2 ABA protocols that are built from local coins. So one is a step optimal broad trust ABA. It only has like half of the running time compared to broad trust ABA, but the message complexity is the same. We also try another thing which reduces the message complexity to quadratic other than cubic. So luckily, it also even has lower running time as well. So in the end, we just put those IBA instances into the PACE framework and implement that as well. So we to make it work in PACE framework, we also need to transform them into Rava. Luckily, we already have some very generic strategies for the transformation, so we were able to do it relatively easily, and we put that into the PACE framework and evaluated the performance. So some quick remark about how it performs in terms of building a really ACS protocol that is built from no cryptographic hash functions. It actually performs pretty well. So for the fully information theoretic ones, where we don't even use hash functions for the performance, the water bear family, like water bear protocols, actually have pretty decent performance. Like when n is very small, like probably lower than 30, the performance is actually pretty close with Beat, the classic BKR framework, right? So I think this part comes from the fact that if we use the PACE framework, we don't need to toss a coin very frequently. If we get really lucky, we don't even toss a coin at all in the failure-free case. So the performance is very close to Beat, even if we use a more expensive ABA protocol. But when n is very large, the performance starts to degrade significantly. We actually provided some latency breakdown in the protocol, I guess. So it was found that when n is greater than like 20, the overhead is all caused by the RBC phase. This is mainly because if we don't use hash function to reduce communication complexity, the running time will be strictly caused by the exchange of the message payload. So when n is kind of large, the one that is built from only hash functions have very nice performance. So that's kind of our conclusion. So the third work I'd like to introduce is our latest work on Fin. I actually presented that last week at CCS. Well, after we finished the PACE framework, one thing we asked ourselves is that can we further reduce the overhead caused by ABA? So one thing that comes to our mind is that protocols in the computational setting all have constant time, right? But protocols in the BKR, like unconditional setting, they only have O log n time. So one question we ask ourselves is, can we achieve constant time for the unconditional setting as well? So our solution is yes, obviously we did that in the Fin framework. So the way how we do the reduction is actually the same for inspired by those in the computational setting. We want to reduce the ACS problem to alleviate multi-value validated Byzantine agreement, right? So in the computational setting, usually the validated part, the predicate that we all need to ask for the protocol is a signature, like in practice, threshold signature. But in Fin, what we did is that we want to use a predicate that is built from an internal state of the replicas instead of concrete signatures, right? So if we use that kind of MVBA construction, we are able to build signature-free ACS in constant time by using this reduction from ACS to MVBA. So our MVBA and ACS roughly works like this, right? So in the first phase, every single replica still disseminates its proposed value using RBC. And then every single replica builds a vector denoting which RBC instances have been completed. So after every single replica holds a sufficiently large vector, it uses this vector as input to MVBA. Now inside MVBA, the predicate we set is that whether those RBC instances have been completed. Right. So if, for example, if we consider the vector provided by P1, for every single replica to consider T1 as valid, it pretty much means that every single replica already delivered some value in RBC11, RBC12, and RBC13. And using the nice agreement property of RBC, this can be achieved relatively easily. So we can ensure that every single proposed value by every single correct replica will eventually be accepted by every replica, right? So inside MVBA, in the end, we decide one of the value proposed by one of the replicas, and we can directly consider the corresponding broadcast value in the corresponding RBC instances as the output of the ACS, right? So that's kind of the nice thing about that. And to make the MVBA work, we actually use the reduction that reduces MVBA to RBC, a common leader election protocol, and RABA. So one thing very nice over here is that still aligned with our observation for pace. If we can ensure that if a sufficiently large number of correct replicas that already entered the election phase, we can ensure that at least F+1 RBC instances, such that at least F+1 correct replicas have completed some of the RBC instance for those F+1 RBC instances, right? So if that makes sense. So in the end, it's kind of the same story, right? So for example, consider the fact that if at least one correct replica enters the election phase, for RBC21 and RBC22, like at least F+1 correct replicas have already completed the RBC instances. If one of the instances is elected in the election function, then the nice property of RABA already guarantees that every single correct replica will output 1. So in the end, we can guarantee constant time, and that's it. Right, so in terms of validity, it's kind of also very straightforward. We only need to ensure that every single input of every single replica already has at least n minus f values. So in the end, we can guarantee the validity property. So in terms of evaluation results, recall that the ABA phase of BKR has 95% overhead, and for PACE, we were able to reduce that to 15% to 80%. And for FIN, we were able to even reduce that to 1 to 5% of the running time. So that pretty much explains why we can kind of build a protocol that is highly efficient. So what we found is that when n is greater than 22, FIN outperforms all previous known protocols in this literature, both in the unconditional setting and computational setting. So for example, for n that is 120 nodes, the peak of throughput of FIN is 3 times that of PACE, 4 times that of spin Dumble, and 8 times that of Dumble. So like, which means that if we achieve constant time, the protocol is quite scalable. But still, when n is like relatively small, PACE is probably still the most performant one. So that's kind of all what we have along the line of ACS. And before I end the talk, I would like to kind of share some of our recent works on POS. It's kind of still a work in progress, and if some, we are also seeking for collaboration because we are quite new to this area. What we started to look at the POS protocol by Ethereum, which is just a new upgrade last year. So one thing we noticed is that there are kind of different attacks, and some of the attacks are proposed by people in this group, and most of them target at things like liveness, chain quality, and things like that. But no one has ever studied the incentive mechanism in POS. And I think, in my opinion, like incentive mechanism is quite unique for Ethereum, because like for a person like me who come from the conventional distributed system community, I found it very interesting to have the incentive mechanism, right? So one thing that Ethereum designs is that it has an attestation incentive, which encourages active behavior. Like if some node votes for something, it can receive rewards. But if it doesn't vote, it will receive penalties, right? So that's kind of one incentive. But other than that, there are many other incentives like stashing condition, transaction fees, things like that. But when we started to look at incentive mechanism, so one thing we ask ourselves is that, can we make honest players suffer from penalties even if they strictly follow the specification of the protocol, right? So even if in a synchronous network, it might be the case, right? So our attack roughly kind of works like this. So we did a series of attacks actually. So our insight over here is that Ethereum utilizes a technique that is quite close to the conventional BFT protocol, right? So one thing very unique is kind of very similar with that in hot stuff. Right? So the idea is it has the last justified parameter over here, right? So the idea is that if more than 2/3 of the replica votes for one checkpoint block, where the checkpoint block is usually the first block proposed in every single epoch, so the LJ parameter is updated. Right, but it's supposed to be a frozen parameter in an epoch. Also, according to the documentation of Ethereum, it's supposed to be not changed at all during an epoch. But in practice, it might be, right? So when we look at the code base of the Ethereum, what we find is that it can actually be updated in any point of an epoch. Right, for example, in the first example, in the figure A, if some replicas receive the first block in an epoch, the LJ is updated to supposedly the first block in the last epoch, right? So it's like the change to block 0. But if the nodes do not receive any blocks at all, LJ is not updated. But in the third figure, for example, it's possible that some nodes receive the block later in an epoch, so the LJ is updated in the middle of an epoch. So that's kind of a very interesting observation. We utilize that observation to make different nodes vote for different LJ. And according to the way how Ethereum fluents the block trees, it's possible that some correct nodes get penalized because their attestations will never be considered valid. So that's kind of the motivation behind here. And I'd like to kind of briefly reveal how it works, right? So we have a warm-up attack where one single validator, under the help of all other Byzantine validators, if they withhold their if Byzantine validators in one epoch withhold their attestations, and the first validator in the epoch is Byzantine, it can release the block later in that epoch. So like assume for example, in the figure B, the first Byzantine validator, PI, it released the block BI later in an epoch. Every single node will update its LJ to a different checkpoint block. Like, so in this example, all the attestations that are marked green, because they vote for different LJ, then what BJ is supposed to be updated. Then those attestations will be discarded, and those correct nodes will be penalized. So that's kind of one idea behind this attack. And we were able to kind of extend that to a full staircase attack, where if all Byzantine validators keep colluding, they can play the game continuously. So in the end, we can make sure that in every single epoch, about half of the honest nodes in the system will be penalized. If we continue this attack looks quite similar with reward attack, and the way how the Byzantine nodes construct the chain is like a staircase. So that's why we call them attack a staircase attack. So what we found is that if the adversary controls 29.6% of the total stake, they can launch the attack continuously in every single epoch. So in the end, in every single epoch, about half of the validators are penalized. So in the end, all honest validators are expected to suffer from no incentives at all. They even suffer from incentive loss. So that's kind of what we observed in our results.
So this means if the adversary controls 30% of stake, they can take away all the voting rewards from all the honest validators, or about half the voting rewards from all the honest validators?
I would say they will not take. So Byzantine validator can still receive their rewards, and their rewards are slightly lower than their fair share. But honest validators suffer from nothing.
Yeah, so the honest validators don't get their rewards for voting, and the adversary loses a little bit, but
yeah, I think we have some concrete calculations about more than 80 to 90% of their fair share. So that's kind of our conclusion. Yeah, so actually we tested that using the Ethereum Prism code base, and we were able to validate our results using our 1,000 validator setting. But we were not able to launch an even larger experiment due to limitation of devices. So we did some theoretic analysis for Ethereum today, right? So Ethereum has a large number of validators. So what we found is that in practice, the feasibility of the attack is limited by mostly two factors. One is the total number of validators. The other one is the maximum number of passations that can be included in every single block. If based on the current parameter setting for Ethereum today, the attack can be launched successfully for like fewer than 16,000 validators. Or if we change the max attestation parameter, if we fix n and for max attestation greater than 2,000, then attack can be launched as well. So we can actually modify our attack a little bit, so the attack can be continued to the next epoch with slightly higher probability. So in the end, I think honest validators are still will still suffer from significant reward incentive loss. Yeah, and that's kind of our conclusion for this work. And I guess that's it for my talk today, and I would like to take some questions.